Welcome to our journey through the cosmos, where we explore the greatest unsolved mysteries of the universe. Imagine a playground, but instead of swings and slides, it's filled with galaxies, black holes, and things that go bump in the night, things we're still trying to understand. Today, we'll dive into dark matter, dark energy, and the Fermi paradox. These are puzzles that have baffled scientists for decades, pushing the boundaries of our knowledge and challenging us to rethink our place in the grand scheme of things. So buckle up, fellow explorers, as we venture into the cosmic unknown. Picture this. You're a cosmic detective, hot on the trail of a mysterious substance that holds the universe together. You've got your telescope, your notepad, and a healthy dose of skepticism. You've been observing galaxies, these swirling cities of stars, and something doesn't quite add up. The way they rotate, the way they move within galaxy clusters, it defies the laws of gravity as we know them. There's something else out there, something invisible, something we can't see directly, yet it exerts a gravitational pull. This, my friends, is the enigma of dark matter. The first clues emerged in the 1930s when astronomer Fritz Zwicky noticed that galaxies within the Coma cluster were moving too fast for the amount of visible matter they contained. It was as if there was an invisible hand holding everything together, preventing them from flying apart. This missing mass was dubbed Dunkle Materie German for dark matter. Fast forward a few decades and astronomer Vera Rubin provided even more compelling evidence. She observed that stars on the outskirts of galaxies were orbiting at speeds that contradicted our understanding of gravity. It was like watching a merry-go-round where the outermost horses were moving just as fast as the inner ones, defying common sense. The only explanation? A halo of invisible matter enveloping the galaxy, providing the extra gravitational glue. But what is dark matter? That's the million-dollar question, or perhaps a billion-dollar question, given the amount of research poured into unraveling its secrets. We know it doesn't interact with light, hence the dark moniker. It's like a phantom, passing through ordinary matter as if it were empty space. Scientists believe it makes up about 85% of the matter in the universe, yet its true nature remains elusive. Some theories propose that dark matter is made up of exotic particles, unlike anything we've ever detected. These hypothetical particles, with names like WIMPs, weakly interacting massive particles, and axions, are thought to interact with ordinary matter only through gravity and the weak force, making them incredibly difficult to detect. The search for dark matter is a global endeavor, with scientists running experiments deep underground, hoping to catch a glimpse of these elusive particles. They're building detectors, shielded from cosmic rays, using ultra-pure materials cooled to near absolute zero, waiting patiently for a telltale sign of a dark matter particle interacting with their instruments. The discovery of dark matter would revolutionize our understanding of the universe. It would rewrite textbooks, spark new fields of research, and perhaps even unlock the secrets to harnessing this mysterious substance. Until then, the case of the missing matter remains one of the most tantalizing mysteries in astrophysics. Our universe is expanding, a cosmic balloon inflating from a tiny point billions of years ago. But here's the kicker. It's not just expanding, it's accelerating. It's like hitting the gas pedal on a cosmic road trip, with galaxies hurtling away from each other at ever-increasing speeds. This unexpected acceleration has puzzled scientists for decades, leading them to propose the existence of an enigmatic force, dark energy. Imagine a force so pervasive, so powerful, that it counteracts the pull of gravity on a cosmic scale, pushing galaxies apart like dots on an inflating balloon. That's dark energy in a nutshell. It's the fuel behind the universe's accelerating expansion, a cosmic mystery that has captivated scientists since its discovery in the late 1990s. The first hints of dark energy emerged from observations of distant supernovae, exploding stars that serve as cosmic mile markers. By measuring the light from these supernovae, astronomers can determine their distance and how fast they're moving away from us. What they found was shocking. The farther away the supernova, the faster it was receding, implying that the expansion of the universe was speeding up over time. This discovery, which earned the 2011 Nobel Prize in Physics, sent shockwaves through the scientific community. It challenged our understanding of gravity, which dictates that the expansion of the universe should be slowing down due to the gravitational attraction of all matter. Something else was at play, something powerful and mysterious, something we now call dark energy. But what is dark energy? That's the billion-dollar question that has stumped physicists for decades. We know it's uniformly distributed throughout space, unlike matter, which clumps together to form stars and galaxies. It seems to be a property of space itself, a kind of cosmic anti-gravity that pushes things apart. One leading theory suggests that dark energy is related to the cosmological constant, a term introduced by Albert Einstein in his theory of general relativity. Einstein later discarded the cosmological constant, calling it his biggest blunder, but it has been resurrected in recent years as a possible explanation for dark energy. Another possibility is that our understanding of gravity is incomplete, and that a more fundamental theory is needed to explain the universe's accelerating expansion. Modified gravity theories such as MOND, modified Newtonian dynamics, propose tweaks to Einstein's theory to account for the observed acceleration without invoking dark energy. The implications of dark energy are profound. If it continues to dominate the universe, it will eventually drive galaxies farther and farther apart, leading to a cosmic isolation scenario known as the Big Freeze. In this scenario, the universe would become increasingly cold and dark as stars burn out and galaxies drift beyond our cosmic horizon. Chapter 3: The Great Silence. The universe is vast, a cosmic ocean teeming with billions upon billions of stars and galaxies. Our own Milky Way galaxy, a spiral of over 100 billion stars, is just one among trillions. With so many stars, so many planets, so many possibilities, it begs the question, where is everybody? This, my friends, is the Fermi paradox, named after physicist Enrico Fermi, who famously posed the question, where is everybody? The paradox lies in the apparent contradiction between the high probability of extraterrestrial life existing somewhere in the vastness of the universe and the lack of any observable evidence to support it. It's like setting up a giant banquet, inviting the entire cosmos, and finding yourself sitting alone at the table. Let's break it down. The universe is about 13.8 billion years old, while our sun is a relative youngster at 4.6 billion years old. That means there's been plenty of time for other civilizations to emerge and potentially even reach technological sophistication far beyond our own. Now consider the sheer number of stars and planets out there. Our galaxy alone is estimated to have billions of planets in the habitable zone, the sweet spot around a star where conditions are just right for liquid water to exist on the surface. Extrapolate that to the trillions of galaxies in the observable universe, and the number of potentially habitable planets becomes astronomically large. So, if the conditions are ripe for life and there's been ample time for it to evolve, why haven't we encountered any cosmic neighbors? That's the crux of the Fermi paradox. It's a question that has haunted scientists, philosophers, and science fiction writers for decades, sparking countless theories and speculations. One possibility is that we are alone, the sole intelligent life in the universe. This is a sobering thought, suggesting that the emergence of life, particularly intelligent life, is an incredibly rare event, a cosmic fluke. Another possibility is that extraterrestrial civilizations do exist, but they are too far away for us to detect or communicate with. The vast distances between stars pose a significant challenge to interstellar travel and communication, even for advanced civilizations. Perhaps the most intriguing possibility is that extraterrestrial civilizations have visited Earth in the past, but we were too primitive to notice. Imagine an ant colony trying to comprehend the construction of a skyscraper. The technological gap might be simply too vast for us to bridge. The Fermi paradox is a humbling reminder of our place in the cosmos. It challenges our assumptions about the uniqueness of life and intelligence, forcing us to confront the possibility that we are not alone in the universe. Thank you for joining us on this cosmic adventure exploring the mysteries of dark matter, dark energy, and the Fermi paradox. We've journeyed to the edge of the unknown, where the boundaries of our knowledge blur and the universe reveals its most profound secrets. Stay curious and keep exploring the wonders of the universe. Don't forget to like, share, and subscribe for more fascinating content.